Hello, in this video we're going to look at flow through a cylindrical tube. So we have this cylindrical tube shown here, the radius of r, and we're going to look at what is the flow in the z direction, this velocity in the z direction, caused by a pressure difference. There's a pressure P0 at z equals 0 over here, and a pressure PL at z equals L. So to solve this problem, we're going to make a few assumptions. So the first assumption is that the fluid is going to be incompressible. This means that our density of the fluid, rho, is a constant. And this is usually a nice approximation for most liquids. A second assumption is that this flow is fully developed. And that means the flow does not depend on the flow direction. So in other words, the velocity in the z direction does not depend on z. The third assumption we're going to make is the axisymmetric assumption. And this means that our velocity and pressure don't depend on theta. So theta is this direction that's not actually captured in the diagram, but it's that third coordinate in our cylindrical coordinate system. It basically means we're not going to get any swirls in either direction through our pipe. The first step in solving a lot of these problems is going to be the continuity equation. And in cylindrical coordinates, our continuity equation is going to be d rho dt plus 1 over r ddr rho r vr plus 1 over r dd theta rho v theta plus one more term, which I'll write on this second line, ddz rho vz, and set that all equal to 0. So we have all these terms. Now we've said that we have an incompressible fluid. So that means this term here we can cancel out. And this also means that we can cancel out all of these different rows within these equations. We've also said that the flow in the z direction does not depend on z. That's our fully developed assumption. So we can get rid of this for fully developed flow. And we've also said that we have an axisymmetric problem. So that can get rid of this velocity in the theta direction. So that leaves us with this one last term, 1 over r ddr rvr is equal to 0. Now we can solve out this differential equation. It's not all that interesting, actually. First, we can multiply both sides by r, get rid of this term, and then we do one integration step to get rid of this ddr term, and that'll give us rvr is equal to a constant. So what does this mean? If you think back to our problem, remember this is a cylinder, and the r direction is pointing outwards towards the surface. So this VR, if VR existed, would be pointing towards the boundary, towards the walls of this tube. And we can think that RVR is going to be equal to a constant. So that means right at the wall of this tube, that value of RVR is going to be the same as the value of RVR somewhere in the middle of the tube. Now at this wall, there can't be any flow pointing through the tube. We can't have any flow through the tube. So that means that our RVR must be equal to 0. And we can solve that out, and VR must be equal to 0 at the wall of the tube, and therefore it must be equal to 0 everywhere in the tube. So we can conclude that RVR is equal to 0, VR is equal to 0. And so what we've basically shown using the continuity equation is that we only have flow in the z direction, since our flow in the r direction is also equal to 0. So our conclusion is only flow in z direction. This will be useful in the next step of our equation solving, in that using the Navier-Stokes equations. So these equations here I've copied from a textbook. These are the Navier-Stokes equations. We have 3 equations to describe this cylindrical coordinate system. And while there are a lot of terms here, if you've solved these problems before, most of these terms we can cancel out. You'll know that we can cancel these terms out. So first off, we know that there's no flow in the r direction. That's equal to 0, so we can cancel out almost all of these terms. There's also no flow in the theta direction. We can cancel out that term. Again, no flow in the r or theta direction. We're just left with this pressure term. Again, I'm just going to cancel out some of these terms because there's no flow in the theta or r directions. Left with only this term. And in the third equation, we do have flow in the z direction, but since it's a fully developed flow, there's no dependence on the time either. So that will go away. We have no flow in the r direction, none in the theta direction. There's no dependence of our flow in the z direction in terms of z. We leave the pressure term. We leave this term because there could be dependence of v on r. We get rid of this term because it's an axisymmetric problem. And we can get rid of this term again because there's no dependence of z, of the velocity in the z direction on z. And so first I'll take a look at these two equations here. This equation in the r direction, this equation in the theta direction. And so we find that dp dr is equal to 0. And note that we don't have any gravity in this equation, so this p is actually our dynamic pressure. So that incorporates the gravitational term in this equation as well. Over here from this theta equation, we can also get 1 over r, again d dynamic pressure, d theta is equal to 0. And so basically this tells us that our pressure is not going to be changing in either the r direction or the theta direction. So we're only going to have pressure impact in the z direction. So now in the next slide, I'm going to take this term right here, the last surviving equation, and try to start solving this problem. The equation from the last slide is going to be d script p dz is equal to mu times 1 over r ddr r dvz dr. To rewrite this, we can actually change these partial derivative symbols into ordinary derivative symbols because our pressure here is only a function of z. This is what we learned from the Navier-Stokes equation. So back here, we found that our pressure does not depend on r, does not depend on theta. So we can rewrite this as dp dz. And similarly on this side, our velocity in the z direction only depends on r. So we can change these partial symbols into ordinary derivative symbols. The other thing we can notice about this equation is on the left we have a derivative with respect to z, and on the right we have a term that's a derivative with respect to r. And the only way for us to have two derivatives with respect to different variables that are equal to each other is if both of these are equal to some constant. And I'm going to call that constant c0. So this actually simplifies our problem quite a bit because we can tackle this in two different equations. We have one equation which is dp dz is equal to c0, and the second equation is this term on the right is equal to c0 as well. So we'll solve this in two steps. First, looking at this term here on the left, and second, looking at this term on the right. So that first equation again was dp dz is equal to c0. We can solve this with separation of variables, so dp is equal to c0 dz. If we integrate this, we can think about our boundary conditions for this problem. So if we return to that original page, our boundary conditions are shown right here. So at z equals 0, our pressure is equal to p0. At z equals L, our pressure is equal to p sub L. So we can use this as our integration. So we're integrating from, on the right-hand side, z equals 0 to L. And on the left-hand side, we're integrating from p0 to pl. So then on the left, we have pl minus p0 is equal to c0 times L minus 0. And we can solve this for c0. We'll need this in the future because that's going to be one of the variables in our velocity flow equation. So we can get c0 is equal to pl minus p0 divided by L. And I'm actually going to rewrite this as a delta pressure. So this is going to be delta p over L. We're going to have a negative sign here. And the reason for this negative sign is that delta p, this term is going to be a positive number. So I can even give this absolute value symbols just to make that clearer. And if delta P is positive, that means that delta P is going to be equal to P0 minus PL. Because our P0 is at the start of our pipe, this is a larger value than our pressure at the end of the pipe. That's why we have flow moving from left to right in that original diagram. So here our pressure P0 has to be greater than our pressure PL if we're going to have flow from left to right. So we've solved for C0. The next step is to go to that velocity profile equation, and then we can plug in C0 into that equation and then integrate that. So I'll jump back here. Here was our equation. C sub 0 is equal to this term over here, which depends on velocity. We'll figure out what our velocity is in the z direction. Here's our equation from that slide, and I can plug in for C0. So C0 is equal to negative delta P, which again, I'll put some absolute value symbols just to be absolutely clear what we're talking about. This is equal to mu 1 over r ddr r dvz dr. The best way to approach this is to try to peel back this derivative symbol one at a time. So each step moving one term from the left-hand side, or sorry, moving one term from the right-hand side over to the left-hand side, canceling these terms out sequentially. A lot of people approach this problem initially when they don't know how to do this by evaluating some of these terms. So they might start taking the derivative, do a product rule across these two terms. That's not the best way to approach this problem. That'll make things a lot more difficult. When the people actually put these equations together in the back of your book, they were doing you a favor by spreading out the derivatives like this, trying to make it a little bit easier to solve some of these problems. So following that idea, let's first move this mu over here. So we get negative delta P over mu L. And then I'll also move the r over to the other side. Times r is equal to ddr r dvz dr. We can integrate both sides. So we have a constant term. This r turns into r squared over 2. And we also have a constant whenever we take this integral. So let's change it to add a new constant here. I'll call that C1. This is going to be equal to r dvz dr. So we just got rid of this term right here. And next we can again divide by r. So let's solve for this last term here. To finish solving this, I'm going to jump to the next slide. Here's that equation from the previous slide. We can do one more step to integrate this one more time. This is basically separation of variables here. So we have on the left side, again, negative delta P over mu L, r squared over 4 this time, plus the integral of this term here, which is going to be C1 times the natural log of r, plus C2 is going to be equal to v sub z. So we basically solved our problem. We just need to figure out what these two constants are going to be. So we can think about what the boundary conditions are for this problem. So let's go back up to this first slide and figure out the boundary conditions. Now, one common boundary condition used in a lot of these flow problems is the no slip boundary condition. So at the wall of our tube, we can say the velocity in the z direction is going to be equal to the velocity of the wall of the pipe, which is 0. So we can say the velocity is equal to 0 at r is equal to capital R. This is one of our boundary conditions. The other boundary condition sounds a little strange until you see the equation and why this makes sense. But what I'm going to say is that the velocity at the center of the pipe is finite. Now this might seem obvious. You're obviously not going to have an infinite flow at the middle of the pipe. So why does this tell you anything? And we'll see from this equation this actually is quite useful. So I'll write down these boundary conditions right over here. To finish solving this problem, we'll need to apply these two boundary conditions. And let's start out with the strange looking one. Vz at r equals 0 is finite. Now if we plug r equals 0 into these terms, we'll get this term is 0. This will be C1 natural log of 0 and plus C2. And if you remember about natural logs and logarithms in general, you know that the natural log of 0 actually goes to infinity. So this is a problem, and this is why our finite boundary condition actually makes sense and helps us solve this problem. we can set C1 equals 0, and then that will just cancel out this whole term, and we won't have to deal with this infinite natural log. So this tells us that C1 should be equal to 0. Now we can use our second boundary condition to finish up the solution to this problem. Negative delta P over mu L capital R squared over 4 plus C2 is equal to 0. So that gives us a solution for C2 is equal to just this set of constants right here. So to finish up, let's just solve for Vz. And this is a good enough solution, but we can actually simplify this out a little bit more and write Vz is equal to pulling out some of these terms, basically pulling out this whole expression on the right-hand side. And that's the solution to this problem. We can group it into this dimensionless group over here, and this group here that has dimensions of our velocity. So first we can check to make sure this makes sense. So if we plug in r is equal to capital R, this term in parentheses right here goes to 0. So that means our velocity in the z direction is equal to 0. So that does satisfy our boundary condition. We can also check that what is the maximum value of our velocity in the z direction? Well, that's when this term here in parentheses is equal to 1. So Vz max occurs when r is equal to 0. And that's this collection of constants right over here. And that makes intuitive sense that we'd have the fastest flow in the center of our pipe when we have no flow on the boundaries of our pipe. Now this equation also tells us the shape of this flow. So if we remember our cylindrical pipe, we know that it has a maximum in the center, and this is quadratic as a function of r. So if here, this is our velocity in the z direction, it'll actually form a parabolic shape where we have a maximum in the center and it goes to 0 on both of the boundaries. I hope you enjoyed this video. Thanks for watching.